All right, here's a little speedy version of 11.3. And where we left off in the past, we have an idea that there are these Taylor polynomials that are tailored to fit to certain functions. These are polynomials that'll fit certain functions, and the polynomials fit for a little while, and then they, didn't quite work out. There were approximations. We truncated, we would say maybe a Taylor polynomial of fifth degree or of 3 terms. Remember, degree and terms don't coincide. A degree is how many derivatives you take in the degree of the polynomial, and the number of terms can just mean I want 6 terms, and the degree could be anywhere from 6 to 10 or beyond. So that's the process we would use to approximate functions, and that's great for especially computing purposes. If we want a quicker way to calculate polynomials, are easier to work with mathematically, even for a computer. And so if you have a polynomial that can approximate e to the x, or cosine of x, or sine of x, and you can exchange that for some code, take a polynomial and exchange it for any e to the x that's in some type of code, it can be a time saver, a calculation time saver, which can add to the performance of a particular piece of software. So now A in this particular example, we did, this is called a Taylor series in 11.3, and the difference between polynomials and series is that series are a perfect fit. So you'll see this equal sign popping up. The function is, this is equal to the function of f of x. The Taylor series is an exact fit, and we'll do some kind of mathematical operations on these Taylor series and show that they perform and act just like the function that they match to, which is another justification for why they are in fact the same function, the series and what you're trying to mimic with the polynomial. So to part B, I got a page coming up here. There is quite a bit of, that part A was pretty slick that we went through and did the ratio test. Now the ratio test, the reason we choose this for the convergence of a series is that it has a nice simple way of showing you when something converges. If we do this ratio test of this function, that is to do the n plus 1th term over the nth term at infinity, we'll find out, it converges if it's less than 1, the ratio, and it diverges if it's not. But we want convergence. We're interested, when does it converge? So if we set it less than 1 and solve for x, because these are situations where we have a variable x, we can actually find out what x's allow this convergence to occur, which gives us an interval of convergence. The interval, one thing we have to figure out is, does it include or exclude the endpoints? And you actually have to test those by plugging them back into the original series to see if it makes a convergent or divergent series. Convergent means you put brackets, it includes the endpoint. Divergent means you exclude the endpoint. Pretty sensical in that regard. So part B, though, this is another one. So we'll finish out the notes on this. Ratio test again. So you take the n plus 1th term over the nth term, and I'm going to have I've just decided to multiply by the reciprocal. So that's one of the wonderful things about the ratio test. Now, I don't have the absolute values in here, but I'll come back and put them in a little later. A ratio test is absolute value, which plays a role, especially when we have an alternator present. But we want to, and this also in this form, I've distributed that power of n, so it's x to the nth over 3 to the nth. It makes this n plus 1 calculation, I don't know, seemingly a little more pictorial and fun, and you can do cancellation and stuff. So if you notice, x on top, 3 on the bottom, because they're each a degree taller than their denominator, and what we get is x over 3 is the result of our ratio test. Now, we set it's not itself less than 1, but we set it to be less than 1 because we want it to converge, and we want to know what x's are going to work. So we actually solve for x, and other times we want it to have x minus center is the format we want to have. But first let's put the absolute values back in there. So here I've solved for x, and often what you do is write it as x minus 0 less than 3. You want to include that center. That's the format we want in these ratio test series convergence tests. Center is 0. We notice that in the very beginning too, the original series doesn't have the x is without any subtracted or added number to it. And then less than 3, if you set it up in this format, the radius of convergence will always be on the right-hand side of the inequality. So the interval of convergence for this, you just take the center plus and minus that radius, and then we put brackets and parentheses at first because we don't yet know whether they include or not, whether it's brackets or parentheses. So here I'm testing -3. I put it back in the original series, and you look at what you get. That's -1 to the nth. And if you go back early on in convergence, divergence, if you go to infinity, that diverges, or if you oscillate, if your value goes back and forth, those diverge, but if it comes to a single number, it converges. Right now, this is -1 to the nth, and if you notice, that just goes to, if you add, this is a sum, if you add those up, we're going to get 0 sometimes, we're going to get 1, we're going to get -1, it just kind of, it'll vacillate between various values. In fact, if you string it out, it's just going to go back and forth between two values, and that's a divergent behavior. We call divergence by oscillation. And there it is. The next one, put 3 in, and I think you can see this coming. It's 1 to the n, and if you add a bunch of 1's together, you get infinity. So this one diverges to infinity, and that's justification enough. So the interval of convergence on this one is not including -3 and 3, so it's just the parentheses. 2c, again, you can go back as much as you want. Remember, videos go a little quicker because you can pause, you can rewind, play it again. You have your computer on, so you can just send me an email, all good stuff. So now, this next problem, there is an oscillator in there. There's that -1 to the n. So when we go to infinity and do the ratio test, we get to ignore it. That's what the absolute values afford us. We're just going to do the ratio test. The n+1th term, I actually have to slip n+1 in there. It's kind of hard to see. So I've done that pictorially there, and then you multiply by the reciprocal of the original. And a little simplifying will get this rolling, so I'll do that somewhat quickly. You can go back and fill in as needed. But if you simplify, those are the terms with the n+1th term, and then you can do some cancellation. Remember with factorials, you can descend factorials and truncate with an actual factorial symbol anywhere you want. So there's that 2n+3 rewritten. And now you're exposing a 2n+1 factorial to cancel with the one in the numerator. And what's left behind are just that 2n+3 and 2n+2 in the denominator. X's cancel nicely. There's 2 degrees higher on top. And if we go to infinity with n, x is along for the ride, but you end up taking x, which is a finite number of some kind. So we're not talking about x at infinity. We're talking about n at infinity, and dividing by infinity makes 0. And that is always less than 1, which is that's for the ratio test. If it's less than 1, it converges. Since it's always less than 1, it doesn't matter what x we choose, then my radius is going to be infinity. If any x works, my radius is infinity, my center is 0, the interval is -infinity to infinity. So we've seen a couple scenarios. We've seen it converge on an interval, tested values. We've seen now if you get something less than 1 with x present, that means, hey, it doesn't matter what x you put in there, this is going to be less than 1. The radius is infinity. It'll converge everywhere. It's a perfect fit throughout the function for whatever function it's matching. Next, part D, there's this n factorial, x minus 3 to the n, little ratio test, how to do it. We've talked a little bit in class. Root test will work. It has the same rules, and it can be a good choice sometimes to get, if you see something to raise to an nth power. This one has got that n factorial that keeps us from using the root test, but I think B would have worked with the root test. But part D, I've got the ratio test going. You can't do the reciprocal stuff because they're just, they're not rational functions. But great cancellation going on there. And remember, n+1 times n factorial, it's the same thing as n+1 factorial, and I exposed that n factorial so I could cancel it with the denominator. And that's what we get. And if we go to infinity with n, we don't get x is along for the ride. Infinity times whatever x minus 3 is infinity. And that'll never, ever, ever be less than 1. So therefore, it doesn't converge for any of those x's. We have to keep in mind, though, for series, they actually converge. Every series converges at the center. It's just in this case, it converges only at the center. If you remember, those are the cases are an interval of convergence. Everywhere it converges, or just at the center it converges. And this is the case of only converging at the center. The radius is 0 when it has the scenario. There is no, radius of convergence is the title for that radius value of 0. It means it doesn't converge anywhere. There's no outside of the center, doesn't converge. So, but you do have to notate the center, which you can actually see in the original part of the problem. X minus 3 means a center of 3. And then the interval of convergence is an empty set, or you just leave it blank. There is no interval of convergence. Example 3, if you're doing Maclaurin, but read the problem, it does say Taylor, so we can't actually use this, but I'm going to write it out. If we were doing Maclaurin and I said, hey, what's e to the 5x? You could do the e to the x, which you've got memorized, right? E to the x series you have to know. And there it is up top. And e to the 5x would simply be substituting 5x in for all the x's above. Voila. And then we could do a nice little run of that. Well, it's also centered at 2, and that's actually what the Taylor series, that's what makes this process I just ran through with Maclaurin, only works for Maclaurin and centering at 0. But for Taylor series, we have to do the nitty-gritty. We actually have to do it by hand. So hang in there while I erase all that poorly. The old-fashioned way, you actually have to go through and do all the derivatives. Now, I'm notating these derivatives in a special way. E to the 5x, its derivative is 5e to the 5x, and every subsequent derivative you have to multiply by 5 because of that 5x in the exponent. So I'm actually writing in an exponential form, and the reason I do that is that if you can pick up on a pattern, rather than expanding those out as 5, 25, and 125, if you leave them in exponential form, you can actually come up with the general term easier. So that's what I'm shooting for. So, and then you put in the center for each of those derivatives, and those are the numerator coefficients for your Taylor series. So here's the Taylor series. I kind of jumped to it to kind of save time. There's e to the 5x, and I put in, if you notice, e to the 10 goes in, 5e to the 10, 5 squared e to the 10, 5 to the cubed e to the 10. Those are the numerator coefficients. And then it's x minus center in each of those to its respective power. So to the 0 over 0 factorial, 1 to the 1 over 1 factorial, to the second over 2 factorial, and so on. And now that I've left that 5 to the n in exponential form, or that 5 squared, I can see that the general formula is going to be 5 to the n, e to 10, x minus 2 to the nth over n factorial. And we found our Taylor series. And the instructions were pretty explicit. They said, please do 4 non-zero terms, 1, 2, 3, 4, and then the nth term. The only thing left for us to do would be to simplify as needed. So things like that first term, we could just go to e to the 10th plus, 5e to the 10th and times x minus 2, etc., and then simplify as needed along the way. Your general requirement, if you were doing this just for a free response, you could leave it as is right now. If you're doing multiple choice, you just have to find a way to match it with the appropriate selection. So to the bottom, example 4, I'm supposed to take the derivative of this, and then f prime of 0. Well, here's the derivative. I went through longhand. All I've done is bring the power out front, so when we have all those x squareds, x cubed, and so on, x squared is 2x. And 2 over the 2 factorial in the denominator is just a coefficient, so it just stays. And then 3x to the second, and so on. But what happens when you take 2 over 2 factorial, those cancel. The 3 over 3 factorial, the 3 cancels with the 3 in the front of 3 factorial, which makes it actually 2 factorial. So here's the deal. We got 1 plus x, and then because 3 over 3 factorial cancels to 2 factorial, now we have x squared over 2 factorial. And if I'd done the 4x to the third term there, if I'd done the derivative of that, you'd see x cubed over 3 factorial, there's 4 terms. And notice we get n times x to the n minus 1 over, now I've written the denominator in this general term in a very special way. Right here, n times n minus 1 factorial. Because if I do it that way, I can cancel those leading n's, and you see that last term there is actually just like exactly the same as our general term below in our original function, back here, so if I circle it, except it's just starting at a different n. If you look really carefully, the f prime looks exactly the same as f of x, except it starts at a different n value. They are the same. So it makes you think, man, what can you take the derivative of and get the same thing? Wait, that's e to the x. I just wrote it a second ago. That's this Taylor series for e. And we're seeing that the derivative of the polynomial is the same thing, just like the derivative of e to the x is e to the x. So we're seeing that that Maclaurin series for e to the x really is like e to the x. Even the derivative behaves the same way. What about the integral? If you flip the page and go to the next one, the integral of e to the x will perform exactly the same way as well. So you'll find that all the things that you know about a particular function, if you do a Taylor or Maclaurin polynomial, to match it, the Taylor and Maclaurin polynomial will have all the same behaviors, integration, derivatives. You can add and subtract, multiply things to it, and it'll have the same effect, stretching, contracting, shifting, etc. That's the story, and hopefully this gets you off on the right foot. Send other questions. There are additional problems that we did toward the back, but those are examples. This gives you the idea of what to do. Those other pages, I'll just hopefully send out plain old notes so you can just see those worked out. Adios.